What happens when I do the algebra instead of in that differential operator setup? I do it with the Laplace transform. Because the Laplace transform actually turns our systems into regular ordinary simultaneous equations. Now, this does mean I'm going to have two Laplace transform objects. I'm going to have the Laplace transform of x, and I'm going to have the Laplace transform of y. But in order to do this properly, I need my initial conditions. These are first order, so I need x of 0 and I need y of 0. And in this case, they're 0 and 1 respectively. So let's start by putting everything on one side of both equations, because that'll make my life easier. Now, rather than rewrite this in that D notation, I want to Laplace transform the hell out of everything. So, back to our Laplace transform sheet. What is the Laplace transform of a derivative? Because I got a derivative right there. Well, in this case, x of 0, but yes. Exactly. Then I get another Laplace of x minus a Laplace of y, and the transform of 0 is 0. Let's do down here. -2 Laplace transform of x. And then here, I do the same thing, but it's now Laplace transform of y, right? So it's minus y of 0 plus s L of y. Now, y of 0 is 1 and x of 0 is 0. So I'm going to simplify this into stuff with Lx and stuff with Ly and numbers. So y of 0 is 1, x of 0 is 0. I have s plus 1 Laplace transform of x minus Laplace transform of y equals 0. And then in Laplace transform of x, I have minus 2 in the second equation plus s Laplace transform of y. And I'm going to take that minus 1, put it on the other side. Talk to me, Jay.
You missed it.
That's an LX, right? So I got S of them and one of them that got combined. These two pieces
we got an X.
become this piece. Yes, that's an LX. This is the Laplace transform of y. Screw the fact that it's the Laplace transform. S plus 1 times thing 1 minus thing 2 -2 thing 1 plus S thing 2. If they were A and B, this is regular ordinary simultaneous equations. This piece of cake. So how do I make this combined? What do I do to eliminate by addition? By elimination by addition. I don't want to substitute. I want to make my life easier. Because this one's negative at the top and this one's got an S at the bottom. Multiply the top row by S. This isn't like a D. This isn't a differential operator. I just multiply an S on. Times S. And I get S plus 1 L of X minus S L of Y equals 0 minus 2 L of X plus S L of Y equals 1. Which means, add those equations together, these cancel. And I get S squared plus S minus 2 Laplace transform of X. Which means Laplace transform X is 1 over S squared plus S minus 2. And now I'm back to doing what I already know how to do. I know how to solve that Laplace transform. What's X? Oh, I got to do all my Laplace transform crap that we were doing last week and the week before. So I need to factor the bottom or write it in one of the ways that it'll show up like this. So does that factor? S squared plus S minus 2? Well, then I'm going to do partial fractions after I write out the factored version. See, I want a minus 2, so I'm going to need a 2 and a 1. I want a plus S, so this should be plus and that should be minus. There we go. Partial fractions time. One over S minus 1 S plus 2 equals A over S minus 1 plus B over S plus 2. What's A, what's B? Please notice I end up with another set of simultaneous equations to solve. I have to solve A plus B equals 0 and 2A minus B equals 1. But this says that A is equal to negative B. So if I put that in here, I get 3A equals 1. So A is 1/3. And then that gives me B equals negative 1/3. Wait a minute. Oh, I have my numbers backwards from where they were down there. B equals negative 1/3. So the Laplace transform of X is 1/3, 1 over S minus 1, minus 1/3, 1 over S plus 2. What's X? Not sure about that one. Right. I found X. How do I get Y? There are at least 3 different ways to get Y. I could, but that would give me a plus C, and then I'd have to do something else to figure out the plus C. So I could do that, but I think that's more of a pain in the ass than it's worth. You're not wrong, because what we have back up at the top is dy dt is 2x. So you're absolutely right, but I think that plus C is going to give me a problem. Because then I could do this and I'd get Y, right? So there are 2 options. There's a third option. The third option is here. I could actually figure out what the Laplace transform of Y is. Because here, this line right here says that the Laplace transform of X is equal to, when I multiply by S plus 1, is equal to the Laplace transform of Y. So I could work from the Laplace transform if you want. This requires me to do partial fractions again. But I absolutely could. I think this is hard because I got to do another set of partial fractions. But I like the other version, Jalen, that you gave me. From the first equation, in which case I just need the derivative of each of these things, right? So there are at least 2 different ways that work well. There's a third way that I have to then figure out what to do with the plus C, and this should work. All right, I'm going to do this one because that's the easiest one. The derivative of e to the t is e to the t. The derivative of e to the minus 2t is minus 2e to the minus 2t. So dx dt is 1/3 e to the t plus 2/3 e to the negative 2t plus x itself, 1/3 e to the t minus 1/3 e to the negative 2t. And that's 2/3 e to the t plus 1/3 e to the negative 2t. Which is the same thing I will get if I do the Laplace transform version. Whew. Talk to me. Because I happen to think this is an easier version of elimination by addition than using the differential operators, D's, that we were using on Friday. But I like the Laplace transform, and I'm a sick mother. That's a separate problem. What do you think?
When you plug it back into like the number eight, do you have to plug it like into the versus the five, five?
No, because I did the X explicitly right here. Once I do the inverse Laplace transform of X, of Lx, this thing, I'm done. Walk away. I got X, I got Y, I'm done.
That is, like, once you get one, like
I can, or I can do the Laplace transform piece, right? Because here, I'd break this up the same way I did up there. I'd write this is A over S minus 1 b over s plus 2, which gives me s plus 1 equals as plus 2 plus bs minus 1, which gives me a plus b times s plus 2a minus b. So this time I have a plus b equals 1 and 2a minus b equals 1 as well. So when I add those, I get 3a equals 1, so I get a is 1/3. And when I put that in up here, I get b is 2/3. So my Laplace transform of y is 1/3 1 over s minus 1 plus 2/3 1 over s plus 2. And when I do the inverse transform, e to the t and e to the negative 2t. I have my numbers backwards. Why do I have my numbers backwards? Oh, because I can't add. Where did I make my mistake? Somebody find it, because it's a really obvious one once you notice it. I was working too damn fast. It's up towards the top of the screen. I added my equations, right? I had those cancel. 1 and 1 is 2. I can do all the crazy stuff. I can't add 1 and 1. Okay, so A is 2/3, B is 1/3. And that's the same thing. Whew. I knew I had to get the same answer. Go through all of this work, Josh, and you can't add 1 plus 1. It's never the calculus problem. Apparently today it's arithmetic. So, Jalen, there are two options on how to get the other equation. And it depends on whether or not the upper original differential equations were quote unquote nice, or if there were major pains in the butt. I think the Laplace transform version's easier to deal with, because I think partial fractions, while it is not terrible, all right, I can do that. Now, it does depend on the actual problem we're doing. And here's something interesting. Excuse me. All the stuff we did last week was first order. Laplace transform doesn't require me to be first order. Laplace transforms can be done with any order derivative I want, because I have that formula with the derivatives. Here it's formula 13 on our formula sheet, and I can do it for any order derivative, which means I don't have to be dealing with first order differential equations if I'm doing the Laplace transform. Here is a second order system. Bleh. All right. Let's Laplace transform this sucker. The Laplace transform of a second derivative is missing something here. I got to have the first value, right? I don't get the Laplace transform until I get s squared. But then I do Laplace of x, and then I do Laplace of y, and that's equal to 0. I do the same thing on the second line, and it's actually the same thing just in y. And the x's and y's are just, oh, there's a sign difference. So I get plus Laplace of y minus Laplace of x. Now we put in all the numbers. What is x of 0? X of 0 is 0. What is y of 0? Same thing. Y prime of 0 is 1. X prime of 0 is negative 2. So those numbers are going to go to the other side. Now, what's on the left side of each of these equations? Let's start with the top equation and gather all our like terms. I have two different Laplace transforms of x. So I get s squared plus 1 L of x. And then I just have L of y in the first equation. In the second equation, I reverse that. I have s squared minus 1. I'm sorry, s squared plus 1 L of y. But I have minus L of x. Okay. I'm looking at my notes. I noticed I made a copy error in this problem. It's just a sign error, but it's still an error, so let's go through and fix it. If this plus y in the first equation, that should be a minus sign, which means that should be a minus sign, which means that should be a minus sign. Fortunately, it's just one sign error, and I caught it early enough that I don't feel that bad. Would have been pissed off if I gotten further through this. Okay. I need to eliminate something. You want to eliminate x's or y's? Okay. If I'm going to eliminate x, then I'm going to multiply the bottom equation by this s squared plus 1. And I get minus s squared plus 1 Lx plus s squared plus 1 squared Ly equals negative s squared plus 1. When I add, these cancel, and I get s squared plus 1 all squared minus 1 Ly equals 2 minus s squared minus 1. I distributed the minus sign there. Which is going to be, wait a minute, that's going to be 1 minus s squared. And over here, what do I get when I multiply this out? But this is already squared, right? So it'll be s squared squared plus 2s squared. So it'll be s to the 4th plus 2s squared. There should be a plus 1 from multiplying this part out, but there's a minus 1 right there. It'll cancel. That'll factor. What I get for the Laplace transform of y is L of y equals 1 minus s squared over s squared plus 2. I just factored s to the 4th plus 2s squared. What do I need to do from here? This is more partial fractions. Yay. Now, you have your choice about how you do this partial fractions because this s is squared. You can either write a over s and b over s squared, or you could write as plus b over s squared. Wouldn't that separate into the same thing? But if the bottom is squared, the top has to be linear. It's got to be 1 power less. Same thing with this part. cs plus d over s squared plus 2. Which means 1 minus s squared is equal to as plus b times s squared plus 2 plus cs plus d times s squared. Now here's where I get to say, I did not do this one this way in advance. So I'm doing this for the first time right alongside you all. I know what the answer should be. I just haven't done this before. Multiply all this garbage out. as cubed plus bs squared plus 2as plus 2b plus cs cubed plus ds squared. So I get a plus c s cubed, b plus d s squared, 2as plus 2b. And some wonderful things happen here. What's the s cubed on the left side? What's the s on the left side? So I know that a plus c is 0, and I know that 2a is 0. Well, that means that a is 0 and c is 0. That was easy. The bottom one gives me a is 0, plug that back in. The top one gives me c is 0. But over here, there's an s squared. So b plus d is equal to -1, and 2b is equal to 1. Well, there we go. That means that b is a half. And that means that d is -1 minus a half, or -3/2. Which means the Laplace transform of y is b over s squared. I'm going to write that like this: 1/2 1 over s squared. Plus c is 0, d over s minus 3/2 1 over s squared plus 2. Out come the Laplace transform sheets. What's the inverse transform of 1 over s squared? Say again? T. So that makes this 1/2 t minus, all right, wait a minute, s squared plus 2 on the bottom. It's one of them. It's either sine or cosine. So I flip back here and I look at sine and cosine, and the s squared plus a squared, when it's an s on the top, is cosine. There was no s, so it's this one, but that needs an a on the top. I'll have an a. I'll have a 1. So in order for me to do this properly, there really should be a square root of 2 up here. And if I need a square root of 2 up here, I need one on the bottom as well. Ta-da! That's y of t. How am I going to get x? Jay, how am I going to get x?
Yeah.
Because back up here, x can be written in terms of y double prime and y. There we go, right there. So yes, I need the second derivative. Y prime is 1/2 minus, there's a sign, but it'll be cosine root 2t, and then there'll be an extra root 2, right? Chain rule, which means it'll cancel the root 2 on the bottom. But that's y prime, and I need y double prime. Derivative 1/2 is 0. Derivative cosine is negative sine. So I get plus 3 over 2 sine root 2t. Oh, right, times another root 2. All I have to do is add those together. X is y double prime plus y. Well, the only part that's going to be a t is this part. So I get a 1/2 t, and then I get minus 3 over 2 root 2 sine root 2t plus 3 root 2 over 2 sine root 2t. Well, that's gross. If I want to add those signs, I need a common denominator here. What happens? What does? Because this number is not the same as this one. You can't cancel them. I have to have a common denominator first. So that means I multiply this by root 2 over root 2, which makes that 3 times 2, which is 6 over 2 root 2. Which means I get 1/2 t plus 3 over 2 root 2 sine root 2 t. By the way, I did this in exactly the reverse order. I got x first and then y from it. Questions? Sometimes you can look at this and say, oh, I don't need the Laplace transform after all. X double prime plus y double prime equals t squared. X double prime minus y double prime equals 2t. Now, I know what happens is we get into the habit of saying, nope, I'm going to do the Laplace transform. I'm going to do the Laplace transform. That's what this whole section is about. Do the Laplace transform. What happens if you add those equations exactly the way they're written?
You,
2x double prime was t squared plus 2t. Or x double prime of t is 1/2 t squared plus t, and you know x prime and you know x. You don't have to do a damn thing other than integrate twice. How about y double prime? Instead of adding the two equations, subtract them. I don't need a Laplace transform at all to do this problem. I just have to integrate. But I need to pay attention to the fact that this is a resolvable equation directly. Okay, why? Where are the places where I'm going to use this? Well, these are all of our models, aren't they? All of our higher degree equations with second derivatives. I need to do what we were doing with the coupled tanks, right? We had one tank feeding into another and feeding back and forth. I should be able to do the same sort of thing with second degree equations. What were our examples for second degree equations? was my favorite example for second degree equations. Come on, people, I brought the rig from downstairs and everything and set it up on the table. What was my favorite second degree? My spring. So I need two springs that interact with each other. And the appropriate idea is a coupled spring. Two springs with two different masses. Gee, I don't know anything that works like this. A seat with a spring on a bicycle with a shock absorber on the tire. You ridden a dirt bike anytime recently? There's your coupled spring system. Or electric circuits. Those of you who will take E&M next semester. Physics 2. There's my electric source. That's my battery. I've got a lamp. I've got a resistor, and I've got a capacitor. Well, there are two different loops and two different connectors here. So I can use my differential equations that we already worked out for the first equation and the second equation right here. My absolute favorite coupled example, and I apologize for not physically bringing the toy with me. I will bring it tomorrow so we can see it in action, is a double pendulum. A pendulum behaves just like a mass on a spring, going back and forth with damping as air resistance kicks in. When I've got two of them, they interact with each other. And the result, quite frequently, is a chaotic system. Now, I don't know how many of you have been watching the newest Jurassic Park BS, but I want you to think all the way back to the very first Jurassic Park movie. You remember this thing? Dr. Ian Malcolm is the math geek. Who's the actor? I've forgotten the actor's name. Now I'm annoyed. What is his theory in mathematics? He's a chaos theoretician. And he's talking about, you put a drop of water on the back of the hand, it runs all these different ways because you can never tell because of how sensitive they are to initial conditions. A double pendulum is exactly that sort of chaotic system. So I hate to break it to you, but this sort of shaking behavior where the masses interact with each other like this on the ends of pendulums can be turned into walls. Your pendulums are rigid pieces. They're the walls. The masses that slide back and forth are the flooring pieces. What happens when you shake the outside? You have an earthquake. Okay, engineers, your building going to stay up or is it going to fall down? Holy crap, this differential equation saves lives.
Does this math have to go with recent Mythbusters?
Hmm?
Where earthquake, like what was it supposed to go?
Uh-huh.
What?
Yes,
It's the same.
it's the same setup. Now, I'll go you one better. Highway 880. You all have computers open in front of you. Google for me. Highway 880, California.
Yeah.
Highway 880 was a two-level road going over the middle of the city. And during an earthquake, it shook. And if the pendulums had been able to take the shear stress, it would have been fine. What happened? Pendulums overshot, the top layer fell onto the bottom layer, fell onto the ground. This doesn't just happen on highways. This happened in a hotel with two suspended walkways. The same thing. I would love to tell you this is useless shit. I don't want to kill people. That's part of why I'm a teacher, not an engineer. But, you know, the electric circuit discussion I had with the people doing the defibrillator project that I was working on in the 80s. Sorry, 90s. That was the beginning of the 90s. Because again, we don't want to kill people. I'm going to put this electrical thing inside your heart and it's going to go zzz, when your heart looks like it's having a heart attack. I don't want to do that wrong. So the applications are huge. And in this case, they're starting to be real. I'll bring my coupled pendulum. I have an even better coupled pendulum. I will also put a discussion of equilibrium up there because we've got another discussion on the general theory, because this idea on systems seems to resolve into doing simultaneous equations a bunch of different ways. Whether we do it with the Laplace transform or not, we're still doing a bunch of simultaneous equations. And damn it, those are matrices. So there should be something in here about matrices. And I want to look at that more closely. That's what I will do Wednesday, because tomorrow is question and answer. For those three sections, all on systems. I will see you all tomorrow. Have a wonderful rest of your day. And I'll bring my toys.